So now, after discussing continuity, we go for differentiability, which we already discussed in 11th standard. Derivative of a function. So let's start with a function here. Let y is equal to fx be a real function. You know, derivative is special type of the limit. So we find this limit f of x plus h minus f of x. What is h? H is any non-zero real number upon difference of these two, x plus h minus x, which is just h, and we take very small value of h, that is we apply limit h tends to 0. If this limit exists, then that limit is called derivative of a function, and you know it is denoted by f dash x. So this is the definition. What is f dash x? It is limit h tends to 0 f of x plus h minus fx upon x plus h minus x. So you will get this. This is called this limit is called derivative of a function, and it is denoted by this. This is also denoted by, you know, change in values of f, that is dy by change in values of x. This is actually x plus h minus x, you know, so this will get cancelled, so upon dx, or it is, you know, f dash x, or it is also denoted by d by dx. This is the operator of fx. So this is read as derivative of function or y, derivative of y equals to fx with respect to x. This we know from 11th standard, right? We had a chapter also. You also know that this can be rewritten in this form also. Limit t tends to x f of t minus f of x upon t minus x equals to f dash x. Both are same. This is just different way of writing the limit. You put t minus x equals to h, so you'll get the above formula. One is this, the other one is this, you know. Okay. This is t formula, this is h formula, remember. You put t minus x, if you take t minus x equals to h, you will get exactly this formula. So this is just different way of writing, both are same. Okay. At fixed point, at point let's say C, we want to write f dash c. So now instead of x you are using c, so just use here c. Limit h tends to 0 f of c plus h minus f of c upon h. This is derivative at a fixed point, remember. This is a general point x, remember. What I did, just in place of x I have placed c. This is f dash c, you know. This is the derivative of a function at fixed point c. Fine, we know up to this. Now here you also know that a method of finding derivative of a function, is called a differentiation, that we know. Differentiation. And if function has a derivative, if a function has a derivative, then it is called a differentiable function. It is called differentiable function. For example, you know x square has a derivative, that is 2x. So x square is a differentiable function. You know tan x has a derivative which is sec square. So sec square is a differentiable function. Tan x is a differentiable function. If a function has a derivative, then it is called differentiable function. So and now I'll take a simple example. You know it, but just to remind you, let's take fx equals to, for example, x square, and we find f dash x. You know it, I'm sure you can do it also, but I'm doing for your information. So f dash x equals to, I'll use that h definition, limit h tends to 0, f of x plus h minus f of x upon h. This is a formula. So this is equals to limit h tends to 0. What's the meaning of f of x plus h? In the formula of the function, you know now composite function. Instead of x, you put x plus h. I repeat, in the formula of the function, in place of x, you put x plus h. So this become x plus h the whole square. Minus, what is fx? X square upon h. Now this is a question of limit. I'll again come to this. F of x plus h means, in the formula of the function, whenever you have x, put x plus h. So it become x plus h the whole square, remember. This is important. Okay, come back to this now. So this is limit h tends to 0. Here just expand it. So x square plus 2hx plus h square minus x square upon h. Okay, so x square will get cancelled. You take h common, it will get cancelled. So here if I take h common, so you have 2x plus h upon h. This will get cancelled. If you apply the limit, this is 0, so you are getting 2x. Right. So what I've shown, derivative of x square is 2x. So this is called differentiable function. So you can write, if you want, we can write like this. Derivative means d by dx factor of which one? X square. So it turns out to be 2x. Like this. This way we can write. You know all these things from the 11th standard. Okay, fine. This just to remind you. Now I'll go to one important result here. Now this result says that if a function is differentiable means what? It has a derivative. That is, I'll write that is, it has a derivative. It has a derivative. Like x square is a differentiable function because x square has a derivative. Sine has a derivative because therefore it is a differentiable function. Cos has derivative. All trigonometric functions are differentiable. Constant function is differentiable because it has derivative. Differentiable means it has derivative. Then it is continuous function. So this is very important result. Continuous function, you know, we did complete exercise. It has a graph without break in a simple language. If function is differentiable, then it must be continuous, remember. Every differentiable function is continuous. So differentiability of a function implies continuity. If you can show that the function has a derivative, then it has to be continuous, remember. Differentiability implies the continuity. You recall x square, you know that it is differentiable. Draw its graph. You know the graph of x square is this. You know that this is a continuous function. Graph is without break. every differentiable function is always continuous. So if I can show that the function is differentiable, it has to be continuous. Now here converse is not true. Here converse is not true. Converse is not true, remember. What I mean by converse is not true, that is, continuous function may not be differentiable. Continuous function may not be differentiable. May not be differentiable. May not be differentiable. Right? You cannot guarantee, it may or may not be, remember. What this says, if function is differentiable, that means it has derivative, it has to be continuous. That means it has a graph without break. But converse is not true. It means if you have a continuous function, it may not have derivative at some point, remember. You cannot say it must have derivative always. So I'll take a simple example. You will realize that function is continuous, but it failed to be differentiable. Derivative may not exist. So I'll come to one example of such function. So now I'll consider this modulus function. This is very standard function, fx equals to modulus function. Right. We know that this is continuous function. We did it. You just go to the session of continuity. We know that it is a continuous function. It is a continuous function everywhere, remember. It's a continuous function everywhere in the domain. You just recall the graph of this function. Union of two rays at origin, if you recall. Like this. Graph you know from 11th standard. This is a graph of modulus function. One ray at origin, the other ray at origin. It has corner here, remember. So this is a modulus function. You can draw the graph without lifting pencil from the paper, so it's a continuous. What we show is here, this is very important, we show that fx equals to modulus x is not differentiable, that means derivative doesn't exist at x equals to 0. This is what we want to show. Right? We will show that derivative doesn't exist at 0, remember. Now, what is derivative? That is the limit only, so I'll write the definition at 0. Okay, so we find this limit here. Which limit? Limit this one only. If you recall, I'll use this formula at 0. I'll put 0 here, 0 here, 0 here. We are finding limit at 0. We want to show that f dash 0 doesn't exist. So I'm writing this limit and we'll show that this limit doesn't exist. Okay. So limit h tends to 0, f of h minus f of 0 upon h. What I did, I've used this limit. Recall f dash c. What is f dash c? It is limit h tends to 0, f of c plus h minus f of c upon h. In this formula, just instead of c, I wrote 0 here. Now, this is equals to, what is this? This is modulus h. What is f of 0? That is 0 upon h. Right? Now you have modulus, so you need to split into right left. You recall continuity beginning. So limit h tends to 0 from right. Here modulus h become h upon 1. Why? Because here h is greater than 0. Why h greater than 0? Because h tends to 0 from right. So modulus h become h. and this limit, this will get cancelled 1. What about this limit h tends to 0 from left? So this is minus h upon h. Why this? Here h tends to 0 from left, so h is less than 0. So what's the modulus h? It is minus h. So this will get cancelled again. This is minus 1. This will get cancelled. This is 1. So what you have shown, limit from right and the limit from left are different, and therefore this limit doesn't exist. And this limit doesn't exist means what? F dash 0 doesn't exist. So therefore I'll write f dash 0, which is equals to limit h tends to 0 f of h minus f of 0 upon h does not exist. This doesn't exist. And therefore what is your conclusion? Therefore you can say that f dash 0 doesn't exist means what? F is not differentiable at 0. You have done nothing, remember. You just obtained this limit, and you at the end you have shown that this limit from left and the limit from right are different. Therefore this limit doesn't exist. Therefore f dash 0 doesn't exist, and therefore function is not differentiable at 0, even though it is a continuous. So what this result says that continuous function need not be differentiable. Where the modulus function turned out to be not differentiable at this point. Here you have corner, remember. Here you have corner. So whenever there is a sharp corner, there the function failed to be differentiable, right? There is a corner at 0 here, so function is not differentiable here, but it's continuous there. So this is one standard example for which function is continuous but not differentiable. I'll show you some more example. If I take fx equals to, suppose modulus x minus 1. You know the graph of this function. Union of two rays at 1. Union of two rays at 1. Here 1. This one ray at 1. This is the other ray at 1 again. So clearly is continuous function. Modulus function is always continuous. It's continuous everywhere. You can draw the graph without break. It's continuous everywhere in the domain. Okay. Now where you have the corner here at 1. So function, your function, you can say that function is not differentiable at 1, remember. Not differentiable at 1, remember, because there is a corner at 1, sharp corner. If I have like this, not then, remember, it should be like this. So here function is not differentiable. Okay, if I take this for example, if I combine these two functions, modulus x plus x minus 1, then if you draw the rough graph, you will realize you will find the corner at here, this is 0, then something like this, and here again corner at 1, like this. Try to draw it, you will realize you find two corners in this graph. One is 0 and the other one is at 1. And if you draw the rough graph here, you will realize here the function is continuous. Without break you can draw the graph, but there will be two corners at 0 and 1. So here function is not differentiable. Not differentiable means derivative doesn't exist. Derivative doesn't exist at 1. Not differentiable at 0 and 1 both, remember. If I have function like this, if I draw rough graph, suppose my function is like this. Zero, here 1, there is a corner, here 2, there is a corner, here 3, there is a corner, here 4, there is a corner, like this. There is a corner at 0, there is a corner at 1, there is a corner at 2, there is a corner at 3, there is a corner at 4. So therefore you can say that function has no derivative at these points, no derivative at 0, 1, 2, 3 and 4. But it is a continuous. You see, if you see the graph, there is no break in this graph, so it's a continuous. So what I'm trying to tell you is continuous function may not be differentiable, whereas if you have a differentiable function, it must be continuous. So with this concept, there is a question in exercise 5.2, question number 9 here. Fx equals to x minus 1 modulus and we show that f is not differentiable at 1. You know it, just now I explained this. Not differentiable at 1. This will show, you know it. Graph is like this. Here 1, there is a corner at 1. So it's not differentiable at 1. Remaining all points it's differentiable, remember. Okay, so we'll show this. At 1 we are going to use the differentiability. So recall this definition. What is f dash c? Limit here h tends to 0, f of c plus h minus f of c upon h. We want to see differentiability at 1, so I'm putting 1 now and I'm writing this. So limit h tends to 0, f of here c, so c is 1, so h plus 1 minus here f of 1 upon h. Okay, this we know here. Here c is 1, remember, so 1 plus h minus f of 1 upon h. Now we put the function value of the function here. So this is equals to limit h tends to 0. What is f of h plus 1? You recall again, in the formula of the function, instead of x you are going to write h plus 1. So modulus h plus 1 minus 1. What is f of 1? It is 0 upon h. I again emphasize on this. Here fx is modulus x minus 1. You want f of h plus 1. So in place of x you write h plus 1. So h plus 1 minus 1. This will go away. This is just modulus h. Okay. So we are left with this. Now this we did before few minutes. Whenever you modulus, you always need to split into right and left limit. H tends to 0 from right, h upon h. Why this? Because here h is greater than 0. Why h greater than 0? Because it is from right side. So modulus h become h. Limit h tends to 0 from left. This is minus h upon h. Why this? H tends to, this is h tends to 0 from left side. Here 0. H is very close to 0 from left side of 0. So here h is negative. You know all these things. So modulus h become minus h. This will get cancelled 1. This will get cancelled minus 1. So what you have shown, this limit doesn't exist. It means this limit doesn't exist. And therefore what is your conclusion? F, and what was this? This was f dash 1, which is equals to limit, you know, h tends to 0, f of h plus 1 minus f of 1 upon h doesn't exist. This limit doesn't exist. Because limit from left and the right are different. And limit doesn't exist means derivative doesn't exist, and therefore f is not differentiable at 1. This is the proof. Solution. Very important example, can be asked in 3 marks. It's just question about limits only from 11th standard, remember. Now this is also very important function, you know, greatest integer function, box function. You know that we already shown, and it was very important example. This was discontinuous at every integer. Now we'll show that it is even not differentiable at 1. That also will show. So let's come back to definition. Again, for your information, recall f dash c, that is limit h tends to 0, f of c plus h minus f of c upon h. We are checking differentiability at 1. So instead of c, I'm going to write 1 here. So f dash 1 equals to limit, as I did in the previous example, f of here 1 plus h minus f of 1 upon h. Okay. So now we find this, and we'll show that this we'll show that this limit doesn't exist. Okay, so limit h tends to 0. Here box of h plus 1 minus f of 1, box of 1, you know it is 1, box of 1 is 1 upon h. So we have this. Okay, now again you have box function, so you need to split into right and left limit. Without that you cannot do this. Okay, so I'll split into 2 limits. Limit h tends to 0 from right, box of h plus 1 minus 1 upon h. Limit h tends to 0 from left, box of h plus 1 minus 1 upon h. Okay, and we'll notice that these 2 limits will be different. So now use this. This means h is greater than 0. You need h plus 1, so I'll just add 1 on both the sides. So h plus 1 is greater than 1. You want box of this, remember. Now this number is more than 1. H plus 1 is more than 1. It's like 1.1, 1.2, 1.3. So what's the box value? It would be just 1. So here box value is 1. I repeat this. H tends to 0 from right. So h is more than 1. I need h plus 1. So adding 1 on both the sides. So this value is more than 1, like 1.1, 1.2, 1.3. And what's the box of 1.1, 1.2, 1.3, which is 1. So this is 1 now. So we are getting limit h tends to 0 from right. This is 1. This was already 1 upon h. Numerator becomes 0. So this limit is 0. So right hand side limit is 0. Come to this. Here h is less than 0. You want h plus 1. So adding 1 on both the sides. You need this much. Now here h plus 1 is less than 1. Less than 1 means 0.8, 0.9 here. This is 1, this values. Here you're 0, this values. So what's the box of this? If I imagine 0.9 here, what's the box of 0.9? 0. If I imagine 0.8, what's the box of 0.8? 0. Less than 1 means first integer from left side, which is 0. So this is 0. So here limit h tends to 0, 0 minus 1 upon h. Now as h tends to 0, this is undefined, so this doesn't exist. This limit does not exist. So LHS limit doesn't exist. Sorry, RHS limit, LHS limit doesn't exist. RHS limit is 0. These two are not equal. So therefore this limit doesn't exist. Limit h tends to 0, box of h plus 1 minus 1 upon h doesn't exist. You know, if these two are equal, then we say that limit exists. So therefore f dash 1 does not exist. And therefore f is not differentiable at 1. Not differentiable at 1. Same way you can try for 2. Not differentiable at 2. Such question is also there in exercise, you can try. Okay, so after doing this differentiability concept, now we list out some standard derivatives which you know from 11th standard. So I'll write here function, and here I'll write derivatives. Each of this we can prove by definition. So I'll start with the first one, fx equals to c, where c is any constant. You know derivative of any constant is 0. So derivative is 0. What is the meaning of this? This means, remember, I'm writing this, d by dx of any constant is 0. Constant means free from the variable. There is no variable here. So derivative of any constant is 0. Next, I'll take fx equals to x raised to n, power function. You know it is n into x raised to n minus 1. What is the meaning of this? This means d by dx of x raised to n is n into x raised to n minus 1. Derivative of x raised to n is n into x raised to n minus 1. This is from 11th standard, remember. Here are two special cases which we use. Instead of n, if I take here 1 by 2, so it is root x, which also we did. Derivative of root x is here 1 upon 2 root x. You know it from 11th standard. One more, d by dx of 1 upon x. X should not be 0. That also we know it is minus 1 upon x square. Right? This is the standard power function, x raised to n, n into x raised to n minus 1. Instead of n, I have chosen here 1 by 2, that is root x. So you put here n equals to 1 by 2, you will realize 1 upon 2 root x. Put n equals to minus 1, so this will be 1 upon x. Put n equals to minus 1, here you will realize it will be minus 1 by x square. So derivative of root x is 1 upon 2 root x. Derivative of 1 by x is minus 1 by x square. Okay. This from 11th standard, remember. Third one, which is I'll list trigo functions. So d by dx of sine x, d by dx of let me write cos x here, derivative of cos, then derivative of tan, derivative of let's write cot, derivative of sec x, and derivative of cosec x. Standard trigo functions. You know all this. Derivative of sine, you know cos x. Derivative of cos, you know minus sine. Derivative of tan, you know sec square. Derivative of cot, minus cos x square. Derivative of sec x into tan x. And derivative of cosec x is minus cosec into cot. This we know. Whenever you again recall, whenever you see first, then your minus sign. Cos minus sine, cos minus sine, cos minus sine. The standard derivatives we know for trigonometric functions. Constant 0, power function, take this power in the product 1 less. For example, if I want to get derivative of x raised to 10, then you know you take 10 in the product, 10 into x raised to 10 minus 1, which is 9. So 10 into x raised to 9. This we know from 11th standard. And then this standard trigonometric functions. This is revision of what we did in 11th. Now I'll list inverse trigo functions derivative. Inverse trigo you have studied. So derivative of sine inverse x, d by dx of cosine inverse x, inverse trigo functions. Derivative of tan inverse x, derivative of cot inverse x, derivative of sec inverse x, and d by dx of, that's the derivative of cosec inverse x. So without proof, this even we can prove by definition. This is 1 upon root of 1 minus x square. Derivative of sine inverse and cos inverse just differ by minus sign. So minus 1 upon 1 minus x square. Tan inverse is 1 upon 1 plus x square. Cot inverse and tan inverse just differ by minus sign. So minus 1 upon 1 plus x square. Then next here, sec inverse, that is 1 upon modulus x into root of x square minus 1. Both x are adjacent here, remember, that way you can remember. Here you have x square minus 1, remember here you have 1 minus x square. And cosec inverse, these two differ by minus sign. Modulus x into root of x square minus 1. Sec inverse and cosec inverse, c then minus sign, here c then minus sign, here c then minus sign. Sine inverse and cos inverse, they just differ by minus sign only. Tan inverse and cot inverse, they differ by minus sign. Sec inverse and cosec inverse, they differ by minus sign. Remember here domain is this, just for your information, x belongs to open interval minus 1 to 1. You cannot take 1 here. Same way here, x belongs to minus 1 to 1 open interval. Your domain is any real number. Your domain can be any real number. Your domain, you know, modulus x greater than 1. This is just for your reference. Okay, so these are the inverse trigo functions derivative. Fifth one, that is d by dx of a raised to x. This is called exponential function. We did it at the end of 11th standard, if you remember, in supplementary material. Exponential function, a raised to x. This is constant, this is variable, like this, 2 raised to x, 3 raised to x, 4 raised to x. Such functions are called exponential functions. A raised to x, and derivative is a raised to x into log this number a to the base e, remember. This is log function to the base e. You know, every log has a certain base. Here base is e. You know, e is a constant. Small e is a constant. All these things we did in 11th, if you remember. E is a constant with approximate value 2.71. If nothing is mentioned as a base of the log function, it is taken as small e, remember. So if I write, for example, what is the derivative of 2 raised to x? It is 2 raised to x into log this number, which is 2, base is e. What is derivative of 3 raised to x? That is 3 raised to x into log this number, which is 3 to the base e. As a special case, if I write here d by dx of e raised to x, this is a standard exponential function. Instead of a, I have taken e. What is that e? E is not just alphabet, it is a constant like pi. You know, pi is 3.14, here constant e is 2.71, approximate value. So what is the derivative? Instead of a, you are going to write e. So e raised to x. And here you are going to put e, so it is log e to the base e, you know it is 1. So derivative of e raised to x is e raised to x. It is actually this, e raised to x into log e to the base e. If these two numbers are equal, you know this is 1. So e raised to x into 1, so we'll get e raised to x. So derivative of e raised to x is e raised to x. Standard exponential function. Derivative of 2 raised to x is 2 raised to x into log 2. We never put the value of log 2. We keep log 2 as it is, log 3 as it is. And finally, now we have logarithmic function. This also, I'm sorry, I forgot to mention, all this you can prove it by definition of derivative. Log x now, logarithmic function to the base e, which is given by 1 upon x, where x belongs to, r plus here. Derivative of logarithmic function is 1 upon x. Base is e, remember. If you have any other base, then derivative may not be 1 upon x. Derivative of log function to the base e is 1 upon x. Derivative of log x is 1 upon x. So these are the standard derivatives which you need to remember.